Hello everyone, in this video we're going to learn about current induction. The first one we're going to go to self-inductance, which is the symbol L, and later on we're going to go to mutual inductance, which with the symbol M. For the first one, which is the self-inductance, the symbol is like this. It looks like a solenoid or sometimes it's a coil because it is actually made of such shape. The unit for it is Henry with the symbol H. Now let's take a look at this circuit. What we have here is a power source of alternating current, and we also have a bulb and a switch. That's it. So let's start with this circuit with no inductor or coil. Let's assume that the current flows in one direction first, like this, and the bulb is light up. Then we add in an inductor or a coil or a solenoid into this circuit. So as the current building up and the current flows into the solenoid or a coil, the magnetic field also starts building up. So as it starts building up, the solenoid or the current or the coil itself is getting stronger. The magnetic field is getting stronger. Now what happened is as the magnetic field is getting stronger, the solenoid itself starts to build up its own direction of current, which is actually opposing the direction of the current flows from the circuit. So this one is what we call back EMF, and the bulb starts to dim. This one, the magnetic field lines starts to getting thicker and stronger and denser. As the current starts to deplete it to go to the other side, we can see that the energy that is being reserved and being stored in the solenoid will use its own current or EMF to use it to flow its own current and making the bulb lit up. So this is what we call self-inductance. It is basically like a charger, like a charger battery, but it's very temporary. Okay, so this is the equation for the induced current. So the induced EMF, so the induced EMF equals to negative L change in current with respect to time. So the negative is to show that the induced EMF is opposing the change in the current flow. Next, we have the equation for the self-inductance for the solenoid, So we have L equals to mu naught N squared E over L. So this one is the number of turns, area, mu naught is the constant, and then length of the solenoid. Next, we have the self-inductance for the coil. L equals to mu naught N squared E over 2R, or sometimes people call it as D, which is the diameter, also can. Next, we have the flux linkage in an inductor, and flux is actually flux linkage. This is sometimes called flux linkage like that, times L equals to L times I. And this is where we get the energy stored, where this energy later on being used because the current starts to flow backwards. So the solenoid or the inductor will start to use its own energy and flow it back to the circuit, causing the bulb to light up. So the energy U equals to half Li squared. Now let's go to the calculation. Coil has a self-inductance of 0.4 Henry. The current through it increases uniformly 2 ampere to 6 ampere in 0.2 second, and we have to calculate the magnitude of the induced EMF. So let's do the listing first. What we have here is the the self-inductance, which is 0.4 Henry. The current through the change in the current is 6 minus 2 because this one is the current final while this one is the current initial divided by 0.2, and then we are trying to get the induced EMF. So we're going to use this equation, EMF equals to negative L, the current over dt. So the answer is negative 8.0 volt. Question number 2. A long solenoid has 800 turns, so N is 800 turns, with a length of 0.5 meters, with a cross-sectional area of 4 times 4 to the power 4 times 10 to the power negative 4 meters squared, and we have to calculate the self-inductance. From here, we can use equation L equals to mu naught N squared A over L. And the answer is 0.643 millihenry. For question number 3, we have a circular coil of 200 turns with and has a radius of 6 centimeters. So number of turns is 200 turns. And then we also have a radius of 0.06 meters. And then I'm going to straight away calculate the area for this one. And the answer is 1.13 times 10 to the power negative 2 meters squared. We have to calculate to get the self-inductance. Again, we're going to use the equation L equals to mu naught N squared A over L. Is 4.74 millihenry. For question number 4, an inductor of 0.25 Henry carries a current of 3.2 ampere, and we need to calculate the flux linkage. So when we do the listing, we have L equals to 0.25 Henry and the current of 3.2 ampere. So we're going to use N flux equals to self-inductance times current. So here we just substitute 0.25 times 3.2, that is 0.8 Weber. Notice that this one is actually the flux linkage or the symbol of like this. And for question number 5, a coil of a self-inductance 0.6 Henry carries a current of 4 ampere. Calculate the energy stored in the coil. So we're going to use the only equation, U equals to half Li squared. Substitute the L and the current, and the answer is 4.8. And because this is energy, we have to use joule as the unit.